Welcome. We're going to continue on here lecturing, and we got into last time chapter 10, I believe. So, chapter 10 was about energy, and again, we were talking about some important types of processes. We talked about exothermic processes, where again, heat and energy is released. We also talked about endothermic processes, where heat is absorbed. And we talked about a couple of different sort of ways that we could kind of calculate energy, if you will. One very common way that energy sort of displayed in chemistry is what is known as delta H. And delta H, again, is what is known as the change in enthalpy. It is basically the heat of a reaction. And one way that you could calculate delta H, as we talked about, is to essentially, for a reaction, take the delta H of all your products and you minus it from the delta H of all your reactants. Remember, as we talked about sort of state functions, and again with state functions, it doesn't really matter how you get there. It doesn't really matter the pathway that you take. Really what's important is sort of where you started and where you ended. And again, as we talked about in a chemical reaction, remember our reactants are really our starting material. And we go to products, which is pretty much where we end. And that's what's formed as a result of that. And that's why when we do something like the delta H, we take our products minus our reactants, again, kind of our final state minus our initial state. Remember a couple things as we did in those examples. You got to make sure that you do multiply the values that you find. And again, these values would be found in a table. And you do have to multiply by the coefficients, which are the moles of each of those. So again, if we were going to calculate the delta H of this reaction, we would take 3 times the delta H value for C that we'd find in the table. We would minus it by 2 times the delta H value for A we would find in the table, plus 1 times the delta H value for B that we would find in the table. So again, you do need to take those kind of coefficients into account when you kind of look up those values and do this calculation. This, again, as I mentioned, is probably the most common way we sort of think about is something exothermic or endothermic. And remember that it is essentially just the sign that's going to allow us to make that determination. So if you have a delta H that's negative, or you calculate a delta H that's negative, that usually means exothermic process is occurring. If you calculate the delta H that is positive, that usually means an endothermic process. So in general, as we talked about, essentially energy and so forth, if you have kind of a more of a negative value that you calculate, it's an exothermic process, energy is being released. If you calculate a positive value, then it's more of an endothermic type process. Now, we also talked about another way to kind of look at heat and sort of energy in a reaction, and that was known as specific heat. And with specific heat capacity, that's the amount of energy that's required to raise 1 gram of a substance by 1 degree Celsius. So the specific heat capacity, by the way, for liquid water, as we talked about, which is definitely a value they do want you to know, is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. I would say most of the time we kind of roll with the joules value. Also a reminder that 1 calorie is 4.184 joules. So that also is like the conversion between the two units of energy. And we could calculate specific heat by going Q is equal to ms delta T. Again, here Q is our heat or energy. It has units of joules, or calories are the typical units that we see associated with that. M is mass, which has units of grams. S is the specific heat capacity, which obviously, as we just saw there, joules per gram per degree Celsius are calories per gram per degree Celsius. Again, oftentimes by students and such, these two guys get kind of reversed in a lot of people's calculations. So again, Q should just have one unit, and the specific heat capacity should have all three. And that's really the definition, by the way, in words of specific heat capacity, the amount of energy, which is joules per gram in degrees Celsius to raise a gram of a substance by 1 degree Celsius. Now, the change in temperature, as we've been talking about, is really probably the most important part of this. This is the final minus the initial. And in one of the few cases, as we talked about, that you do leave it in degrees Celsius because our specific heat capacity is in degrees Celsius. So unit-wise, everything cancels out. As we talked about, Q also, if you have a negative value of Q, we're looking at an exothermic process. And if you have a positive value of Q, an endothermic process. So as we talked about last time, it is this part of that calculation that will determine whether or not you'll have a positive or negative number, as the temperature will be a reflection of what is happening in terms of that substance and in terms of energy. Is that substance gaining energy, or is that substance losing energy? And a reminder that if a substance is gaining energy, our heat, typically what you will see is the temperature will start to rise, right, as a result of it gaining that energy. And vice versa, if somebody is releasing that amount of energy or releasing energy in an exothermic process, they're going to essentially cool down. So we will see their final temperature actually go lower than they started with. And that's really what's going to give us a negative value for Q and an exothermic sort of process that occurs. We finished up, I think, talking about the idea of this sort of transfer of energy. And remember that because we do know the specific heat of liquid water, it is oftentimes used to figure out how much energy is being released, for example, in a reaction, or if you want to know something about how much energy, say, a piece of metal is being released. Like we talked about last time, if we had a piece of metal that was at a higher initial temperature than, say, our water's initial temperature here of 25 degrees Celsius, when we throw that in there, in this particular example, it is the metal that's going to release all that heat and energy to the water. So again, for our metal, it's an exothermic process in this example. And for our water there, it's an endothermic process. It's going to basically absorb all that heat and energy. The result of that is we will see our temperature in our water increase, say to 27 degrees, for example. And what we will see for the metal is its final temperature will actually come to rest at the same temperature as the water, because frankly it's sitting in there. So they'll equilibrate to the same temperature. So it will drop to, say, 27 degrees Celsius. Once again, because we know everything for the water, we would know the mass, we would know the specific heat capacity, and obviously we would know the change in temperature. That would allow you in this example to figure out how much energy the water actually absorbed. Again, in this example, not always the case. It could be the opposite way around, but in this case, it would be absorbing energy. And because of that, and what we've been talking about in terms of this sort of transfer of energy, which is, it is sort of a perfect sort of transfer of energy. All the heat that the water gained had to come from one source, and in this case, it's the source of the hot metal. So the amount of energy that was gained by the water should be the exact same amount of energy that was lost by the metal. The only difference is, as we were talking about, it's a exothermic process for the metal, while it's an endothermic process for our water. So we get this sort of relationship we sometimes use, which is Q of the metal is equal to negative Q of the water, which means, let's just say hypothetically here, we calculated Q and it was 1200 joules, just as an example. And that is how much energy was gained by the water. If we want to know how much energy was lost by the metal causing that change, it would be the exact same number, except it would be negative 1200 joules to indicate that it's being released. And that works well, as we talked about. For example, if you solve for something like the specific heat capacity of a metal, This would be negative in this case of this example, and our change in temperature will yield us a negative difference, and that's going to again turn our specific heat capacity into a positive number. So again, those negatives are kind of important here. Remember that if you're calculating anything involving energy, do not just discard the negative sign for the energy value or heat value, because again, it does indicate endothermic or exothermic, and it's really important in terms of the answer. Now, in this particular case here, again, the metal is actually hotter than the liquid water. Remember, it would be opposite if we, for example, took a piece of metal out of the freezer and the initial temperature of the metal was -3 degrees Celsius, and our water here was initially 25 degrees Celsius. When we would go actually put that metal into that water, because the metal is actually colder, it is actually the metal that's going to accept all the heat and energy from the water. Again, heat always flows from hot to cold in this case. So it would be the opposite effect in this situation. The metal would be a positive value for Q, and actually the water would be a negative value for Q. So again, although a lot of times people kind of focus on this direction of the flow of heat and energy, you could also look at the opposite flow, and it could be in the opposite direction as well. So the thing to remember, as we talked about, is again, it always flows from hot to cold. So that should be the direction of whoever's going to release the energy should usually be the hotter temperature, right? And the colder temperature should be the one absorbing the energy. Any questions on that? Yeah. Yeah. It does in this particular equation, and the reason for this equation and why it has to be is the specific heat capacity values. And if you look at specific heat capacity values, they're in degrees Celsius. So in chemistry, we actually roll with those guys for specific heat capacities. It's one of the few places where we actually don't convert our temperature to Kelvin. If you do it in physics, they actually do it in Kelvin, usually in a lot of cases. But here, for some reason, we still roll with the degrees Celsius one. So in this case, it's probably the one few case you wouldn't convert it out, so that everything cancels. Yeah. I just made it up actually. I said just for this example, I just made it up. So, yeah. So for example, it would have came from, for example, if you use this equation and we had numbers, I just made up the Q just to indicate. In my very first example, because the metal was hotter, the water would be gaining energy and it would be a positive number. And again, the metal in that case would be a negative number. Yeah. It's specific heat capacity in general, or specific heat in general, because the table, for example, if you look in your book, and that table we saw the other day, those values are in degrees Celsius is the units of specific heat capacity, the S in there. So if you change your temperature to Kelvin, then you're going to be, it won't cancel out correctly. You'll get the wrong answer. So outside of this equation, probably in this class, and probably maybe most of the chemistry classes you take, it's a pretty safe bet to go to Kelvin. Yeah. But this is the one place where don't go to Kelvin, because you'll, you should not, because in, I would say 99 times out of 100 in chemistry, you're going to have this unit in the specific heat capacity. So I won't say 100% time. I didn't write the book and all the problems, but if you see in your specific heat capacity, it's actually in Kelvin, which is very uncommon for chemistry, then you should convert it. In physics, they kind of do it with in Kelvin, but usually in chemistry, they keep that one as degrees Celsius. So you want to keep the temperature there. Yeah. 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 No, sometimes you may be solving for the specific heat capacity. Like we did in that little problem at the very end last time. We used the water to figure out the actual specific heat capacity of the metal. Or you could just have a straight up problem where, frankly, you could think of this as a formula where really you could solve for anything in that formula. So it is potentially possible. You are responsible to know here at the school the specific heat capacity of liquid water, that 4.184 joules per gram per degrees Celsius. That will not be given to you. And I would say in a lot of problems, sometimes they won't give you that number either, like in homework problems and stuff like that. And sometimes you may have to look up on a table or something, a specific heat capacity problem. So if you come across a problem like this, for example, and you're looking maybe for mass or something, and you're like, you have this, and you're like, I'm still kind of missing that, you may have to go look it up for whatever you're dealing with in that situation. But definitely you should know that 4.184 number. Yeah. Other questions? All right, so this is just a relationship like we were talking about. Again, that perfect transfer of energy should result in a zero amount of heat that has been lost in this case. So this is basically Q for our water equals this guy, and this is Q for our metal here. But remember that if you do this, you can bring this entire thing to the other side, but you do have to distribute a negative sign. You need that negative relationship. So you can set, for example, Q of the water, which is equal to ms delta T equals Q of our metal, which is equal to ms delta T. And remember, you do have to kind of distribute that negative. So if you set these two guys equal to each other like it is up there, sort of, you do need that negative that needs to be distributed. Otherwise, you will get a wrong answer on one of those sides. Yeah. Yeah, so like I said before, this is the specific heat capacity. It's the same thing as S, and then some books will use SH as well. I can't remember off the top of my head your book whether you use C or S, but that's basically the specific heat capacity. So sometimes people will use some different symbols. I personally use S for that, but sometimes people will use C to represent that, and that would be like the 4.184 number that we talked about. Yeah. Other questions? All right, so why don't you try one here and see what you come up with. We have a 110 gram sample of a metal at 55.5 degrees Celsius. It raises the temperature of 150 milliliters of water from 23 to 25.5. What is the specific heat of the metal in joules per gram per degree Celsius? So take a few moments there, see what you come up with here. Okay, so let's take a look, see how you're doing. So again, we have a very similar example to what we've been talking about. So we have a piece of metal here. And obviously for our metal, the mass is 110 grams. The temperature of it initially there is 55.5 degrees Celsius. And it raises the temperature of 150 milliliters of water, and that's a volume. Obviously, our water here. And it goes from an initial temperature there of 23 degrees Celsius to a final temperature of 25.5 degrees Celsius. And we're looking for our specific heat capacity of our metal in this case. So as we talked about before, as we know, when that metal goes into here, the metal is actually again at a hotter temperature than the water initially. So we should expect here, right, the metal being the one that's going to release the energy. And we also know that once we put that metal in that water, it will eventually come to rest at the same temperature, right, as the water. So we will know that the final temperature of our metal will be the same temperature there of our water. Any questions on that there? The thing that we always know about liquid water is, and again, maybe not always given to you in a problem, we always know the specific heat capacity of liquid water, which is our 4.184 number. So in this situation, we basically, once again, have enough information about the water to figure out, in this case, how much energy the water is going to absorb from the hot piece of metal that was put in it. We do have one other issue, which is this is not a mass, but it is a volume. And we could do that pretty easily because another number that you need to know, right, and we talked about earlier, is when necessary, the density of water is basically can be used as 1 gram per milliliter. So that is what we could use here to convert our volume into a mass, and it is going to give us basically 150 grams of water. So it's going to give us basically the same value here since the density of water. So remember, if you come across a problem much like this that involves water and you need a way to go from like volume to mass, 1 gram per milliliter is a value that you can always usually use. Now that we have that, for our water, we pretty much have all the information we need to solve for, as I mentioned before, how much energy our water is going to gain. So the mass of the water is 150 grams. Specific heat capacity of our water, 4.184 joules per gram per degree Celsius. And again, final temperature, which is 25.5, minus initial, which is 23.0 degrees Celsius. Let's kind of go down a little bit there. And if we do that there, we are going to end up with, not that number, let's try the right number, 4.184. There we go. Times 150. We're going to end up with 1,569 joules, as the grams will cancel. Again, degrees Celsius here going to cancel, and we are going to be left with joules. Again, significant figures like we talked about last time. This is 4 sig figs, right? This is 4 sig figs. And here we're subtracting, so we are looking at decimal places, and that is a 2.5 degrees Celsius when we do that. So technically speaking, that's about where this number should end. Once again, what I commonly would do is not really round at this point because we're not really done with the problem here. So I'm going to continue on with the whole number. But again, as we talked about, I think at the end last time, you do got to kind of keep track of everything throughout your calculations, right, to end up in the right spot. So what I know is that amount of energy that was absorbed by the water, that 100% came from our metal that we put in there. So the amount of energy that the metal lost in that case would be, once again, the exact same number of energy that the water gained, except it's going to be negative in this case because it's exothermic for the water. So again, the value is the same. The sign changes to represent that it's releasing that energy and it's giving it off. Any questions on that? So now when we look at our metal, we're good to go because now we have pretty much everything we need to solve for what it's asking for. We now have the Q of the metal, we have the change in temperature of the metal, and we have the mass of the metal. So we could solve for S, which is our specific heat capacity. Remember here we're multiplying, so we're going to divide those guys to the other side, do the opposite move. So S would equal Q of the metal divided by M delta T. Putting in our value here, negative 1569 joules, divided by the mass of the metal, which was 110 grams. And also really important here, right? Final minus initial for the metal. And in this case, that would be 25.5 minus 55.5 degrees Celsius. This number here again is going to give us a negative value, which is necessary to turn our S into a positive value. So I think we get something like 30.0 negative. And again, that negative there and this negative here will turn this guy into a positive number, which it should be. And again, that's what we're looking for. So once again, I'm going with the whole number there, 1569 divided by 110, divided by basically 30, I think, in this case. And again, on this case, we're going to get a 0.4754545. The units, by the way, do not cancel. Joules, gram, degree Celsius, they all stay there. And we do leave the number with the top unit. Now, this is where we want to kind of clean it up to write sig figs. So once again, back here, this number up here should actually be 2 sig figs. This should be 4 sig figs. And obviously our subtraction where we go to decimal place is 3 sig figs. That means, technically speaking, based once again off the very first calculation we did, we actually should end up at 2 significant figures in this case. And we would need to round up. So 0.48 looks like. joules per gram per degree Celsius in this case. Any questions? Yeah. I put the line there because that's just to remind me, and you don't necessarily have to put the line there, but it just reminds me that technically I did this calculation right here first. And technically speaking, when I would do that calculation, we're multiplying all the way across there. Obviously, we're subtracting out the last part of it. So we would do the subtraction for first, which would give us 2.5, which technically is two significant figures. And that times this number, which is four significant figures, and this number, which is four significant figures, means that when we're done with just that part of the calculation, if we were going to wrap it up and kind of give that as an answer, it actually should only go to two significant figures. So that is where I'm trying to keep in my head, okay, I'm going to continue on with that number, so I'm not going to round at this point. But technically speaking, when I went down here, technically speaking, if I did round, it should have been something like 1600, which has only two significant figures. And where that comes into play is now I'm really taking two significant figures divided by four significant figures and three significant figures. That means when it's all said and done, I should end up at 2, which really came from the very first part of the calculation. So although we do look at the last part of the calculation that we talked about last time as really determining where you should end up, that could be based on the previous calculation, right? Because those numbers that you used in the last calculation came from a previous calculation that you guys keep track of. Yeah. So is your question just like, how do I know it should end up at 2?
Why? I mean, I guess for the 1569, the two significant figures. So you're saying, like, why did we not do, like, in my brain, I did when I was calculating for the specific heat capacity of the metal, I looked at those three numbers and I was like, okay, so we're multiplying and dividing. So the least significant figure is 3. So I was going to put 3.
Yeah, so the specific heat capacity of water is 4.184, so that's four significant figures. And since we're multiplying and are dividing, you look at the smallest number of significant figures. And in this entire calculation that's in a box, yeah, it's always whatever you're doing in terms of the calculation. You have to look at all the numbers that you need to look at. Unless it was an exact number, then you wouldn't need to look at it.
Decimal figures, and then look through all the numbers in the problem and find one.
Yeah, so it's always the least, rather either way, if you're adding or subtracting, decimal places are significant figures, it's the least. But again, as we talked about last time as well, you want to do kind of the math order correct. So really the first thing that you would do would be the subtraction. And we would go to the smallest number of decimal places, which is 1. It just so happens if you just took 25.5 minus 23.0, you end up with 2.5 as the number. Yeah. And that number does go to 1 decimal place, but now we have to look at that number as to how many significant figures it has, because the next thing that we did was multiply all the way across, right? So now we need to switch from decimal places to looking at significant figures, and still that 2.5 has the least number of significant figures now compared to the other, which means technically the answer we get there should have 2.
Okay.
Yeah.
So one, like one significant figure, where the problem up there, and how to achieve that one.
You would in that case. Again, remember the only thing that you would not look at is if something is considered an exact number, yeah, or definition or something like that. Yeah. I'm sorry, I missed the first part. The first part was if the gram number was exactly. So it just so happens this in this case is based off of the 2 that came from the first part of the calculation. But let's just say hypothetically speaking, obviously it won't come out right, but you just say this was a 5 or something like that, and it had 1 significant figure. At this point, you would then compare the last calculation. You would have 2 significant figures divided by 1 divided by whatever that last one was, 3. You would go to 1 in that case, yeah. So it is definitely based on the last one, but you do have to still take into consideration all the calculations you did previous to that. And it is definitely possible that the last calculation will have a smaller number than maybe something you did previously, and you can continue on and do it that way. Other questions? Yeah. All right, then let's talk a little bit about energy and nutrition as we sort of touched upon previously. Remember that a calorie with a capital C is a nutritional calorie, and that actually is 1,000 of the little calories, or a kilocalorie. So one nutritional calorie, which has the capital C, is 1,000 of the little calories with the little c, and 1 kilocalorie. Now, a calorimeter is something that we use to, for example, you could use it to measure the amount of calories there are in food. You could also, like you'll do probably Thursday, you could use some coffee cups and use it to measure out some reaction and heat. So this is what is sometimes referred to as a bomb calorimeter. It's an isolated condition or container. It basically has water, and you put something on there like your chocolate chip cookie. There's oxygen in there and there's some wires to ignite it. So basically what happens is once you ignite it, your cookie goes on fire. Obviously that's going to release heat and energy to the surrounding water. And since this is an isolated system, there's no influence from energy from outside or the surroundings. And you could basically just follow the temperature change of the water and pretty much roll with our equation we just did, and you can figure out how much energy the water gained. And in this case, right, your cookie would be the thing that supplied the energy. And from that, you can figure out how many calories, regular calories, that was absorbed by the water, that was lost by the cookie. And you can turn that into nutritional calories and figure out how many calories were given off, nutritional calories were given off from something like a cookie. Now, when we talk about food and energy, there's 3 types of food that we deal with: carbohydrates, fats, and proteins. And each of these have a caloric value. And you could use the caloric value of carbohydrates, fats, and proteins to basically determine, like I said, how many nutritional calories there are, for example, in a serving of chips or cookies or whatever you may be eating. And you could do that by basically just taking the kilocalories times those caloric values. Now, for carbohydrates, it's 4 kilocalories. For fat, it is 9 kilocalories per gram. And for protein, it is 4 kilocalories per gram. So, for example, if you look on a back of a nutritional label of some type of food product, you usually will find those 3 categories listed, and they'll say maybe there's 4 grams of carbs in that substance. And maybe they'll say there's 10 grams of protein. And maybe they'll say there is 6 grams of fat. And if you look on that nutritional label on a piece of food or a food item, you basically could just multiply each of these by their caloric value. So 4 grams of carbs, we would take 4 kilocalories per gram. For protein, also 4 kilocalories per gram. And for fat, it is 9 kilocalories per gram. And basically the grams cancel. And this will give us that our food in this example here is supplying 16 kilocalories for our carbohydrates. It is providing 40 kilocalories for our protein. And for our fat, it is providing 54 kilocalories. Remember that a kilocalorie is a nutritional calorie, so that's basically how many calories you're getting for each of those products. And basically, if you just add all those guys together, a little 54 plus 40 plus 16, not too bad. 110 calorie snack pack there, right, is what this imaginary food I just made up would be providing to you. And that's where they get, if you look on the labels, the nutritional labels, it says how many calories per serving. That is essentially how they get those numbers, yes, sir. I'm going to say probably don't worry too much about them, yeah, in this case, yeah. But that, again, is sort of where you get those things. In my experience, usually they'll round down if you actually do the calculation yourself. I imagine there's a reason why they round down usually in a lot of cases. Now, when we talk about constant pressure calorimetry, like I said before, this is something that you could do in lab, and we'll do in lab, I think, maybe tomorrow. And you could really do a lot of these type of experiments to figure out things like enthalpy and energy by simply just 2 coffee cups, 3 coffee cups, and a lid, and a thermometer is really all you need. And because we can basically follow what's happening with water, either it's absorbing water or releasing energy, the water's either absorbing the energy or releasing it, we can really figure out how much energy is being given off. And if you do this under constant pressure conditions, your Q will equal your delta H at constant pressure, which is in most cases, the pressure doesn't change all that much in the room you're doing it in. So that usually is constant pressure type situations. Now, as I mentioned before, we oftentimes in this class talk a lot about, putting a piece of metal into the water, and that's something like you're going to do as well. But you could also do just regular old reagent type reactions. You could take like an acid and a base, put it together in the coffee cup and follow the change in temperature, and you can relate it to a acid-base reaction. Again, the reason you're usually able to do that is, as I mentioned previously, I think, those are what are referred to as aqueous solutions, and a solution is a homogeneous mixture. And since aqueous is a lot of times water-based, you basically just assume the specific heat capacity of water, and you can do your calculations, and you can actually figure out the delta H. And if you knew how many grams of something you started with, you could figure out how much energy per gram or joules per mole. You can figure out a lot of energy by simply just a little bit of coffee cups and a thermometer and a lid, and you could do a lot of reactions in that. Any questions on that? Now, I will say that the bomb calorimeter that we saw in the previous picture, sometimes people will actually introduce the specific heat or energy of the calorimeter itself. And I say that because you might come across a problem maybe online or something where they talk about that. We're going to not involve any type of calculation that involves like taking into account the calorimeter's specific heat and heat of the calorimeter itself. So don't worry about that if you do come across a question. I think there might be one or something like that where it kind of talks about the heat of the calorimeter itself. We're not going to worry about that. Yeah. The closest you get to is, I think, what you're doing tomorrow, which is the coffee cups. Yeah. So I mean, it is, and it is a calorimeter, and it works really well. But we won't. That's as close as you kind of do it. Yeah. 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 All right. I think we kind of did an example of that, so we'll skip this one. It's not super important. All right. So the last thing we're going to talk about in terms of energy is actually equations and how energy is related to these equations. Now, when you have an energy value like delta H, you can change the delta H value if you have to do something to that equation. So what I mean by that is a couple of things. For example, if we have this equation where water, which is ice, goes to liquid water, we have a delta H as positive 6.01 kilojoules per mole. That actually is something we'll see in a later chapter. That is the delta H of fusion, or the heat of fusion. That's the energy required simply to do that process right there. Take something from solid to liquid, basically. That's the amount of energy you need just to simply do that. Let's just say, though, you were interested not in it going from like ice to liquid water, but you were interested in the opposite way, going from liquid water to ice. A reminder that we reverse the reaction here. So from here to here, we reverse the reaction. And what happens to the sign is we actually change the sign. So if you have a reaction that has a delta H value associated with it, and you change or reverse the reaction, what happens to the delta H value is the sign changes. Why does that happen? It's based on how we calculated delta H is products minus reactants. So if you change and reverse the reaction, your products are now your reactants are now your products. The difference is the same, but the sign will change. So if you reverse a reaction, the sign of delta H will change. Other things that you could do sometimes to a reaction is maybe you don't just need one of something, but maybe you need two of something. So you can multiply that entire equation, the first guy here, by 2. And this gives you this equation here. What that does to the delta H is you would then multiply the delta H value by 2. So you can also multiply it by 2, and it changes it. The last thing that you could do to these equations is you could divide by a common number. So let's just say you didn't want 2 of everybody, but you wanted 1 of everybody. You could divide everybody by 2. That would put you back up here. And if you divide by 2, you would actually take the delta H and also divide it by 2. So if you reverse the reaction, the delta H sign changes. If you multiply by a common number, you take the delta H and you multiply by that common number. If you divide that reaction by a common number, you take the delta H and you divide it by that common number. So these are the ways that the delta H value, it changes as you change the actual reaction. Yes, sir. What's that? Yeah, so it's the coefficient. Yeah, so, well, yeah, it would sort of be the coefficient. Maybe not always coefficient, but it's basically the factor by which either you multiply or divide it by, for example. Yeah, yeah. So in my example there, it would be 2, basically. It would be the factor. Yeah. 12.0 is 3 significance of that. Is that your question? Yeah, yeah. No, it's 12.02 would be 4 significance. Yep. Now, what are some other ways that we could use something like this? So for example, let's just say, we'll just take this one here. We'll take the water example here. Water going to water. And our delta H is 6.02 kilojoules. So you could actually come up with conversion factors from an actual equation. So for example, the coefficient here is 1, and the coefficient here is 1. And we could actually say, for example, for every, these coefficients, as I might have mentioned last time, do represent the moles of these guys. So you could say, for example, for every 1 mole of water in the solid state, I get out 6.02 kilojoules of energy, basically. And that could give you 2 conversion factors. 1 mole of ice over 6.02 kilojoules of energy. Our 6.02 kilojoules of energy is 1 mole of ice, right? So these are 2 conversion factors you get from the equation. You could also do it for the products as well. If I produce 1 mole of liquid water, I would produce 6.02 kilojoules of energy related to that, and you get a similar type of conversion. So for example, if I had 4 moles of ice, and I want to know how much energy I would get, I could use this as a conversion factor, and I could go 4 moles of ice. And just like dimensional analysis, right, we're going to go opposites cancel. So moles of ice is on the top, which means we would need moles of ice on the bottom, which would be this conversion factor here, 6.02 kilojoules per 1 mole of ice. And that would get us 4 times 6.02. It would tell us that we would produce, in this case, 24.08 kilojoules of energy, and we would perhaps round it to 24.1 kilojoules in this particular case. And we can do it as a conversion factor. So from an equation, you could actually get some conversion factors that you use that are energy and sort of product type ones. We're not going to talk about another too much right now because it's a different chapters like chapter 8 where we talk about it, but I am just going to show it just for a second because again, they probably assume maybe that you've seen chapter 8 since you got to chapter 9. So there is something known as molar mass. And molar mass comes from the periodic table. And you could get it from the number that's on the bottom. And for example, if we look at hydrogen and oxygen, and you look on the periodic table, these are the numbers that you see basically on the bottom of those elements. And molar mass has units of grams per mole. And you could think of molar mass like a conversion factor as well. You could use it at grams per mole. You could also use it as moles per gram. So for example, if we had our equation we were just looking at, and we will definitely talk more about this in the appropriate chapter when we get there, but and let's just say instead of I gave you the moles to start with, like we just did, you're giving grams of water. So just to say you had 45 grams of water, and you want to know how much energy, you would produce in this sort of reaction. So, and again, we'll go with solid, obviously ice in this case. So what we would want to do is, because our conversion factor that we had on the previous slide is in moles, right? 1 mole of ice gives us 6.02 kilojoules. Our 6.02 kilojoules gives us 1 mole of ice. This molar mass that you could get from the periodic table is essentially the conversion factor that allows you to convert from grams to moles and backwards. And that is the molar mass that basically allows you to do that. So in this case, I really can't use this value the way it is because the value that I need it in is moles. So one of the things you sometimes will have to do in a problem like this, for example, is take the molar mass of water. So how do we calculate the molar mass of water? We essentially just add up all the parts. So there's 2 hydrogens. The number here always goes to the guy to the left. And if there's nothing written, it is a 1, right? So normally we don't write 1 in chemistry. So if there's nothing written there, it is assumed to be a 1. So we would have 2 times 1.008 grams per mole. And again, this is coming from the periodic table underneath hydrogen. And that would represent my 2 hydrogens in water mass. I would then add it to my 1 oxygen, which would come from here, which would be 16.00 grams per mole. And basically I just add it together, and that would give me a molar mass of water of 18.02 grams per mole. When you calculate molar mass, and again, we'll talk more about it in the appropriate chapter, you usually go about 4 significant figures, and you usually pull from the periodic table about 4 significant figures. So that number is underneath the symbol. Again, sometimes you may have more or less than that, but usually 4 is what you want to go for. So now that I have this as my conversion factor, again, I can use it just like a conversion factor of 18.02 grams per mole, or I can put the moles on top over 18.02 grams. So if I take my 45 grams of water, which is obviously ice in this case, and I use my molar mass just like a conversion factor, grams are on top. I want to get rid of grams, so I'm going to put grams on the bottom. So moles of water per 18.02 grams. The grams are going to cancel. We're going to multiply and divide like our normal dimensional analysis we've been talking about. So we're going to go 45 divided by 18.02 gives me 2.497 moles of water in the ice state. Now again here, I'm not going to round right now. I'm going to kind of take the whole number, but here I should be looking at my 3 sig figs. This is really considered an exact number. You don't have to really worry too much about that. So really I should end here is kind of where that number should end. Now that I have it in moles, I could use, just like I did previously, my conversion factor from the equation that has the energy. And I could go 1 mole of ice from the equation gives me 6.02 kilojoules. And now I could take this number, I'm going to take the whole number and multiply it. And now I'll end up with 15.0 kilojoules of energy, would be absorbed in this case. And again, this is sometimes a common sort of calculation. They sometimes will give you the value not in moles, but in grams. And you do have to do that grams to mole conversion so that you can use the conversion factor that you get from the actual equation. Question on that. And again, it's actually chapter 8 where we talk about grams, moles, and all that kind of stuff. So we'll get there eventually. But again, since it's chapter 10, you might come across something like this. Yeah. Any questions on that? Yeah. It was from the actual equation that we were looking on the previous slide. So it's from here. And I use that as a conversion factor, from that equation. By the way, if I was doing this exact same calculation for 45 grams of liquid water going to ice, what is the only thing that changes? Yeah, it would end up being, instead of 15 positive, it would end up being 15 negative, because basically this would then be negative, right? If we were going the other direction, and that would be basically the exact same number, just a different sign. Any questions on thermal chemistry type of equations? All right, that wraps up chapter 10. Okay, we're going to continue on here. So we're off now from 10 back to 4. So in chapter 4 here, we're going to talk about the atom. We're going to talk about periodic table, ions, and some properties of the atom here. So let us get going here. First, though, with formulas of compounds, and we sort of touched upon this in some of the other chapters, but a reminder that a compound always contains basically the relatively same number of atoms of each element present. And as we talked about last time, really the difference between sort of a molecule and a compound is a compound does need to have multiple elements involved, while a molecule doesn't. A molecule could be the same elements. Atoms of the same element are different elements. But for it to be a compound, it does need to be atoms of different elements involved. Like water always contains 2 hydrogens and 1 oxygen, no matter where you get it from. We do write a chemical formula by using the symbols for each of the elements. And we do put subscripts next to them to indicate how many of each of those. So when we do see something like water, like we just talked about a second ago, the subscript on the bottom does always go to the guy to the left of it. And a reminder that if there is nothing written in a subscript, it does mean 1. And again, in chemistry, we typically don't write 1 for most things. So if you don't see a number, it does represent that there's 1 of them. So this would mean, as we did there when we just calculated the molar mass of it, it does have 2 atoms of hydrogen and 1 atom of oxygen in this particular case. And again, that's what makes it a compound, because it has atoms of both hydrogen and oxygen, 2 different elements that are involved. We never, use big numbers or anything like that. So always subscripts there. To the left, if we had CO2, we would have 1 carbon, 2 oxygens, C2H6, 2 carbons, and 6 hydrogens. So again, that is always the way that we sort of write chemical formulas. Each atom is represented by its chemical symbol, and those subscripts, as we'll talk about as well, again, symbols for chemicals or elements up there are either 1 letter or 2 letters. So also a reminder that if you are writing a symbol for an element, you do want to go capital first letter, lowercase second, if it is a 2-letter symbol. So you do not want to do capital on both of them, because that does not mean the same thing. Top guy is cobalt, which is an element. Bottom guy is carbon monoxide, which is not cobalt for sure. So when you write symbols, if it happens to be a 2-letter symbol, first one capitalized, second one is not. If it is a 1-letter symbol, like we have a lot of them up there, it is just a capital letter is what we use for the symbol, like K for potassium, C for carbon, and for nitrogen. So if you have a 1-letter symbol for the element, should be capitalized. If you have a 2-letter symbol, first one capitalized letter, second one lowercase letter in that particular case. As we just saw here, this would mean 1 nitrogen and 3 hydrogens in this particular case. And we did these a second ago, 2 and 1, 1 and 2 in this particular case. All right, so take a moment and based on the description there, write a formula, a chemical formula for each of these guys, these compounds. Okay, so let's take a look at the first one, a molecule that contains 6 carbon atoms and 6 hydrogen atoms. So symbol for carbon is C, and 6 carbon atoms should have a 6 next to it. And hydrogen symbol is H, and it also has 6, so we should have C6H6. A compound that has half as many calcium atoms as chlorine. So calcium is capital C, lowercase a. And if I have twice as many chlorine as I do calcium, chlorine is capital C, lowercase l, and I would need a 2. Again, 1 calcium for 2 chlorines in this case would be our proper formula. Lastly, a compound that has equal numbers of sodium. Sodium is capital Na, and nitrogen, which is capital N, and 3 times the oxygen, which is O. So since each of these are 1, 3 times would be 3, and it'll give us NaNO3 in this case, or sodium nitrate, calcium chloride for the middle guy, and some benzene there for the last guy. Any questions on any of that there? Okay. So what we're going to talk about now is the atom and what makes up the atom and some important experiments along the way that led us to maybe a better understanding of the different parts of the atom. As we go through it, we'll talk about what obviously you need to know from those experiments and stuff like that. But we're going to really talk about the atom here and sort of its sort of structure. So it all started a long time ago where philosophers really expressed the idea that matter is composed of these very small indivisible particles, which they name atomos, which means uncuttable or indivisible. And a lot of things became very clear as time went on from that point, that most natural materials are mixtures of pure substances. Remember, as we talked about in the previous chapter, a pure substance can be an element or a compound. So if you have like pure water, it's a compound. If you have pure iron, it's just iron, obviously, as well. One of the important laws is the law of composition, and that means that a given compound will always contain the same composition regardless of where it comes from. So for example, there's 8 grams of oxygen for every 1 gram of hydrogen in water, and that is, as we saw, H2O. Each hydrogen is about 1 gram, as we calculated a second ago. So that's about 2 grams, give or take, of hydrogen. And each oxygen is 16 grams, right, per mole. And that's approximately for our oxygen. So if I take, obviously, 16 divided by 2 gives me an 8-to-1 ratio there. So again, for every 1 gram of hydrogen, I have 8 grams of oxygen that is there. That is always the situation for water, no matter where you get your water, no matter what bottle it is. The water part of it is always that ratio. So things are always put together in simple ratios, and they always come together by mass in the same sort of ratio. Yes, sir. No, there is. So you could definitely have other ratios of or proportions of elements that come together, even the same elements. And we'll actually see it in just a few minutes or a few slides down the road. But for example, you could have nitrogen and NO, you could have NO2 and so forth, and they will always come together and sort of, as we'll see in a second, the simplest whole number ratios is sort of how they come together. So it would be wrong in the sense of the mass for water ratio. Yeah.
Definition of it, you have there, it's always the same composition definition? What is that? A little more?
Yeah, it basically just means that if you have water, which is ultimately H2O, no matter where that water comes from, no matter what sort of form it's in, for example, it could be solid, liquid, right, or gas, it will always have that mass to mass ratio of basically for every gram of hydrogen you have there, you have about 8 grams of oxygen with it. Yeah. Other questions? Now, one of the first sort of ideas about the atom and what's known as Dalton's atomic theory was made by a guy named Dalton. Dalton was an interesting guy. He kept weather records for most of his life. He never married. He did like to go bowling on Thursdays, and that's an important piece of information. You never know when that'll pop up. So it is Thursdays, not Fridays or Wednesdays or half price Saturdays. But really, besides going bowling on Thursdays, one of the things that he is known for is he did come up with a theory about what we call atoms. And let's go through some of the important parts of Dalton's atomic theory, which you do need to know. First off, he had this idea that atoms are these sort of indestructible sort of things. And he felt that elements are composed of extremely small particles called atoms. He said that all atoms of a given element are identical, having the same size, mass, and chemical properties. Remember that one of the things that makes something a theory is the idea that it may not be correct in all aspects. So a theory is something that can be revisited, and some things about a theory may work and some things may not work. And again, that's different than a law, which it always does the same thing always over and over again. Now, for Dalton, this right here is one of those things that has been later found not to be correct. And the existence, as we'll talk about, of what are known as isotopes, basically make this part of his theory incorrect. And isotopes, as we'll talk about later on, actually in this chapter, is the same element, but they have different masses. And that obviously is different than what he said. He said, again, all atoms of a given element are identical to each other. So the existence of isotopes that were discovered basically disproves that part of his theory. He did say that atoms of one element are different than atoms of another, and that is true. So if you have a copper atom, it has different properties than, say, an iron atom. So they have different protons and perhaps neutrons and stuff like that. He said that compounds are composed of atoms of more than one element, and as we've been talking about, that is correct as well. And a chemical reaction only involves the separation and recombination of these elements or atoms. We don't lose anybody along the way. We don't gain any elements along the way or atoms of those elements. Basically, as we'll talk about in a chemical reaction, all you do is just break everybody apart, and then you kind of reassemble everybody on the other side into new compounds. And that is why, for example, when we get to balancing equations or writing equations, that is why you balance an equation, because if you started with 4 carbons on the left-hand side of the arrow, you should still have 4 carbons when it's all said and done on the right-hand side of the arrow. They just may be in different compounds. So we never ever change elements in a chemical reaction. And as we go through this chapter, we'll explain why that happens and why we have really the conservation of elements as we go through that. And that is the law of conservation of mass, which means that matter is never created nor destroyed. And the idea there is, for example, if you had 4 carbons on the left-hand side of the arrow and end with 4 carbons on the right-hand side of the arrow, because each carbon is 12.01 grams, you will basically end up with the same mass of carbon on both sides because you will not lose any sort of ratio. Any questions on that? So the existence of isotopes means that that part of his atomic theory is not correct. Also, the idea that atoms are indestructible. And the idea of that is also kind of disproven with nuclear reactions. In nuclear reactions, you can change an element from one element to another. So that also is something that is not correct. Now, one of the ways he pictured compounds as collection of atoms, here we have NO, NO2, and N2O. So for example, if we just take these two guys here, atoms basically come together in certain proportions, and they come together in certain proportions that are equal to each other. So for example, this is one nitrogen at 1401 grams from the periodic table, 16 grams from the periodic table for oxygen. And if you do the relationship of, say, oxygen to nitrogen in mass, you take 16 grams divided by 1401 grams, that gets you something like 1.14 ratio. Now, if you take NO2, which is 14 grams for nitrogen, 2 times 16 grams, since we have two oxygens here, gives you 32 grams. And if I take the oxygen to nitrogen ratio here, we have 32 grams divided by 1401 grams gives us 2.28 as our ratio. The difference between this guy and this guy is we have twice the amount of oxygen, right? The difference in the ratio is 2, right? So again, they will always come together in these sort of equal proportions of elements when they do come together. We always get things come together in whole numbers. We never get like a half of atom or anything like that. So they do come together obviously as whole atoms. And the ratio of how they sort of come together is always the same in terms of their mass as well, because they have the same situation. All right, so let's talk a little about the structure of an atom. Based on Dalton's atomic theory, it was, and by the way, you do need to know the parts of Dalton's atomic theory, and obviously know, as we talked about, what is maybe not correct, about the isotopes and the atoms of the same element being identical to each other. A lot of investigation was done from 1850 to the 20th century, and was found that although atoms are really, really small, they do contain an internal structure that's even smaller, and these are what are sometimes referred to as subatomic particles. And investigations have led to the discovery of 3 types of subatomic particles. Electrons, which you may be familiar with, are negatively charged particles. Protons, which are positively charged particles. And neutrons, which are neutral, have no charge. So although atoms are extremely small, they're made up of these even smaller components, are protons, electrons, and neutrons. And we're going to talk about sort of the experiments that led to the discovery of each of these subatomic particles. Do you have a question, sir? Yeah, okay. Yep. So the first thing that we're going to talk about are electrons, and sort of the important experiments that led to their understanding. Now, some of the really important things in terms of these investigations that were done early on does involve a couple of things that we've mentioned before, just to reiterate, is that idea of opposites attract, and that is sometimes called electrostatic attraction. And again, things that are positive and negative are going to be attracted to each other. They are going to want to kind of attract one another. Things that are negative and negative, or things that are positive and positive, will repel each other. Now, a lot of experiments used radioactive particles, and we'll talk about some of those, but just some of the radioactive particles that were used. For example, alpha particles, and these are positively charged radioactive particles. They're essentially helium. You'll sometimes see it written like that. There's also beta particles, which are negatively charged radioactive particles. And it's essentially an electron, and sometimes you'll see it written or symbolized like that instead of the beta symbol. And there's also gamma rays. And gamma rays are basically have no charge and are pure energy. And one of the things that a lot of these experiments that we will see as we go through it took advantage of is the idea of things that have a charge. And there are a couple of things that you can use that to your advantage. For example, if you had an electrical field, you have a positively charged guy and a negatively charged guy, you could use something like an electrical field to figure out how particles would behave. So for example, if I had an electrical field and I shot a particle and it bent up towards the positive plate of the electrical field, we would probably think that that particle should be what type of charge? Yeah, it should be negative charge, right? It's going to be attracted. If we shot a particle and it kind of bent towards the negative plate, we would think it would be a positively charged particle. And if we shot a particle and it basically was unaffected by the electrical field, if I could draw a straight line, we would expect it to have no charge. So electrical fields, also magnetic fields, which have a north pole and a south pole, kind of work similar. Were used a lot in some experiments, along with radioactive particles that have charges that allowed people to take advantage of those properties of opposite attracts to each other. Now, one of the biggest sort of advantages or movement towards understanding the electron came with the invention and the use of what is known as a CRT. And a CRT stands for a cathode ray tube. And that was a really big sort of step forward in terms of understanding electrons. So this is sort of a schematic of a CRT tube. It has basically a negative side and a positive side. And inside are negatively charged things like electrons, are particles. And because these guys are negatively charged, we would expect these particles to head towards the positive side here of our tube, right? And away from our negative side because it doesn't want to be near there. And by doing this, they oftentimes will put some type of coating up on the end there, and you could actually see where the beam's actually hitting as it goes through there. And the CRT tubes, maybe you've seen them, I don't know, old TVs that have backs, not flat screens, really old ones. Used to be on the ground, people used to have them, right? Take off the back of it. Old computer monitors that have like a really big back that comes out the thing, not these. But those were CRT monitors, and picture tubes inside a traditional old time television were like CRT type of tubes. Now, like I said, it has a negatively charged particles like electrons that are emitted, going away from the negative side of the tube to the positive side of the tube. And again, some type of fluorescent material there, sometimes put on there so that you could see it. And again, as we just talked about a second ago, taking advantage of the idea of things with charges, using an electrical field or even a magnetic field with a north and south pole, we can sort of understand what type of particles we're dealing with. Again, this guy kind of floating towards the negative side would be more of a positive. This guy going to the positive side, more negative, and a neutral guy heading straight through. So, I think it's this, maybe one more. So here is an actual cathode ray tube. We'll play this, see if it plays maybe.
A cathode ray or Crookes tube. It produces a beam of electrons.
Try that again.
This is a cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So you can see the bright spot there is your ray, your negatively charged particles, affected obviously by the magnetic field that is going to it. And you used to call a TV repairman to fix your picture tube if your TV went out. You didn't just go buy a new one and stuff like that. All right, so that was a really big sort of invention that allowed, for example, one of the first important aspects of understanding the electrons, which was done by J.J. Thomson. And J.J. Thomson used a cathode ray tube, as you can see there, him sitting in front of it. And he was able to obtain properties of the electron, and he was able to basically get the charge to mass of an electron. And that is right here. It is minus 1.76 times 10 to the 8. C is a coulomb. It's a unit of electrical charge. And G is grams, which is obviously a mass. So coulomb charge to mass of an electron. So the first thing that you should know is Thomson used a cathode ray tube to figure out the charge to mass of an electron, and that was a good forward step to understanding electrons. The next sort of experiment that sort of complemented what Thomson was doing and helped us get an even better understanding of the electron was an experiment that was done by a guy named Millikan. And Millikan did what is known as the oil drop experiment, and it is kind of what it sounds like. Basically shot oil droplets in to this chamber, had a little hole, and they would start to fall based on gravity, but this chamber had an electrical field, and it would pick up a charge as it's falling, these oil droplets. And what Millikan was able to do was to adjust the electrical field in such a way that the oil droplet basically just hung there. It didn't go up, didn't go down, just kind of hung there. And from that, he was able to figure out another really important aspect of the electron, which is the charge of an electron. And there's an example of that experiment. It starts to drop, adjusting the electrical field, and you can see the oil droplet just kind of hangs there. So Millikan was able to determine the charge of an electron, which is minus 1.6 times 10 to the minus 19. So these two experiments were really important for the electron. We have Thomson, who figured out the charge to mass of an electron. We have Millikan, who figured out the charge of an electron. And if we use both of those experiments together, sort of the outcome of those experiments, if we take the charge and divide it by the charge to mass of an electron, charges cancel. From those two experiments, basically the mass of an electron was able to be determined. And if you do that calculation, the mass of an electron is 9.09 times 10 to the minus 28 grams. So that is the mass of an electron. And again, sometimes you'll see it as to the minus 31 kilograms instead of grams, but it's just a gram to kilogram conversion. That is a large number, small number. That is a pretty small number, right? It's like 28 places to the left and put a bunch of zeros, right? So it's a relatively small number. So the first thing that we learned is electrons are negatively charged from these experiments. Again, Thomson, using the CRT tube, was able to figure out the charge, the mass of an electron, followed by Millikan, who did the oil drop experiment, that was able to figure out the charge of an electron. Put them together, we now are able to figure out the mass of one of these subatomic particles, which make up an atom of a particular element. Any questions on that there? Now, moving forward, after sort of the electron was sort of hammered down, if you will, by the early 1900s, two areas of the atom was pretty clear. They contained electrons, which obviously was discovered through some of those experiments we just talked about. And they were also found to be electrically neutral. So if we know that they contain electrons and they are negatively charged, they do have to contain something else there that is positively charged to allow them to be neutral, right? So if you're neutral, that means you have no charge. So all your positive and all your negatives should basically cancel each other out. So around the turn of the last century, the accepted model of the atom was one that was proposed by Thomson. And basically he said that the atom was this sphere of positive charge. So in this atom, we have this big old sphere of positive charge. And inside the sphere of positive charge, he felt that the electrons were embedded inside. So you have these electrons embedded inside. The atom was made up of these negatively charged electrons. This is what is sometimes referred to as the plum pudding model of the atom. A plum pudding is like a kind of pudding rice type dessert with raisins embedded inside. So like all the pudding rice part was like the positive charge, electrons kind of in there embedded inside is like the electrons. And a much nicer picture of it there, as you can find in your book, looks something like that. Again, we have this positive charge which is spread way out all across the sphere. We have these negatively charged electrons that are embedded inside. And again, in this model of the atom, it was assumed that most of the mass of the atom is actually made up of those electrons. So this was sort of an accepted model of the atom based on the information that was known at the time. And then came along really the big experiment, if you will, that really changed the idea of what an atom kind of looks like. And with this accepted model of the plum pudding model, we have our next really important experiment, which is what's known as the gold foil experiment. And the gold foil experiment was one done by a guy named Rutherford, along with a guy named Geiger, for like the Geiger counter when you use radioactivity, and a guy by name Martian, but most of the people just go with Rutherford. Rutherford used very thin pieces of gold foil, and he shot alpha particles at them. So a reminder that our alpha particles are these positively charged radioactive particles that he shot at pieces of gold and other metals as well. Now, what Rutherford assumed would happen, and actually what Rutherford saw happen during his experiments, are two different things. And what Rutherford was going off of was really this plum pudding model. And again, in this plum pudding model, this is all of our positive charge here. And what he anticipated was he was going to shoot these alpha particles, which are heavy, positively charged particles that are moving pretty quick, right? So they're moving pretty fast. And what he expected to happen was, as he shot these positive particles essentially at positively charged atom, he expected them to kind of pop through with some deflection. It would be, for example, like if I took this piece of paper, I held one side really tight, and somebody else held the other side really, really tight, and this was all my positive charge all through here. And if I shot like a pen through this, right, moving really fast, and if both sides were really, really tight, right, the pen probably would pop through and with a little bit of deflection, right, as it kind of pops through, but it should be able to kind of go through it with no problem. And that's essentially what he thought would happen based on this model of the atom. What he actually saw when he did it was something that was kind of surprising to him. He actually saw that his alpha particles sail through pretty much undeflected. It didn't have any problem, and they just kind of went right on through. But what he did witness, though, was every so often, these alpha particles would get scattered at really large angles and maybe even come back to the source at which it is at. And that made him think that maybe this model is not so correct. right? So clearly there's some reasons why that happened. And he had to kind of go back to the drawing board of the atom based on of his findings. So one of the things we should think about is if these alpha particles went through undeflected, no problem, just sailed right through, what did they hit? They probably hit nothing, right? So if I took my pen and just tossed it that way, there's nothing in the way, right? It's just going to go right on through, no problem, right? So that means that most of the alpha particles that he shot at the atom didn't hit anything. They just kind of sailed right through. But he did witness that every so often those particles would bounce off at a really, really large angle. And since alpha particles are positively charged, what type of thing would make it bounce off at a really large angle? It would also have to have what type of charge? It has to be very, very positively charged, right? Because if it hits something that was very positively charged, it's going to go and bounce off at really, really large angles. If it was negatively charged, it would actually just stick, right? So it wouldn't go anywhere. So it had to hit something that was really, really positively charged. So if you take my example, I won't ruin my periodic table, but if instead of our positive charge being spread out, right, all through the entire atom, if I took my positive charge and I did the folding move, right, and you just keep folding it and folding it, right, where they say like 7, 8 times is as many times you can fold something, right? And now if all my positive charge, right, is all concentrated right here, and I shoot my pen at it, it is definitely not going to go through, right? It's going to actually probably bounce off like you would see. So the results that he saw was really surprising for him. That really led to us understanding that this plum pudding model is not necessarily the correct model of the atom based on the results that he saw. So let's take a look at that. I think I've got a little video here maybe. There it is.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle. In 1910,
So as you can clearly see,
angles.
as you can see, most of them just went straight through, but every so often you can see a highlight on the screen at different locations. And again, that would be it hitting something very, very positive. And as I mentioned, that was really surprising for Rutherford based on the plum pudding model that kind of going into the experiment, that's sort of what he assumed the atom looked like. So he said, you know, it's kind of like if you shot a gun at a piece of paper and the bullet just came back to you. That was very not what they were expecting to sort of happen. So as I mentioned before, what he essentially needed to do was throw out Thomson's model and really come up with a new model of the atom. And the new model of the atom is really the sort of current model of the atom. He said that the atom is mostly empty space, and it is mostly empty space. And that does make sense based on the idea that most of those alpha particles sail through, right? So nothing was in its way and nothing was too problematic. It does contain a very dense positive core, which is a nucleus. And in the nucleus, which is positively charged, that is where we find, as we'll talk about later on, protons, which are positively charged, and in 1930, neutrons, which have no charge. So typically speaking, the atom, empty space, we have the nucleus where protons and neutrons are really housed. And really in that empty space is where we find electrons. And electrons are flying around fairly randomly about the nucleus. Is there going to be attraction between the nucleus and electrons? The answer is yes, right? Because electrons are negatively charged and the nucleus has positively charged protons. So there is going to be that attraction. As we'll talk about in the later chapters, That is why certain electrons, for example, are involved in bonding and other ones are not involved in bonding depending on where they are relative to the nucleus. And one of the other major differences between sort of the plum pudding model and really the current model of the atom is most of the atom mass is the nucleus. So unlike in the plum pudding model where they felt most of the mass of the atom was the electrons, it's actually the nucleus where most of the mass of the atom is, and that's because it has protons and, as we'll talk about, neutrons in it. So empty space, we have basically our nucleus, protons, neutrons. We have our electrons, by the way, as we'll talk about, moving around fairly randomly about the nucleus. They don't move in pretty circles or anything like that. They move in a pretty random amount. There is, again, some attraction between the nucleus, which has those positively charged protons, and those negatively charged electrons. Any questions on that? So you do need to know Rutherford's experiment. You need to know kind of what he thought was going to happen, obviously what did happen, and obviously now the correct model of the atom, if you will, the difference between the plum pudding and the current model. Yes, sir.
Where it goes, like
The CRT tube shoots negatively charged particles, and well, that's one way you could take advantage of using something like an electrical field or a magnetic field. Is if something does have a charge, it will be affected by that. And the CRT tube and Millikan's experiment use that to their advantage to understand some properties of electrons. Yeah, so you need to know a little bit about kind of what he did, not super great detail, but a little about what he did and what came out of those experiments. Thomson, Millikan, and obviously the Rutherford experiment, along with obviously what the plum pudding model was, right? And the current model of the atom, which is what we just talked about, mostly empty space, and most of the mass is the nucleus, which is positive.
the charge, no, it's not the deterrent, the charge of particle, the negative.
It is something that was used to help determine the mass of an electron and explore really the electron. And here's a summary table of some of those things of what, kind of the highlights of what you should know from those experiments here. You don't have to worry too much about the first one. We could just basically kind of start it there through here. And these are sort of the important outcomes of sort of what happened in those things. Yeah. All right.
It's exactly.
No, you just kind of need to know. I'm probably not going to ask you, what the charge and that type of stuff is. I would say they probably expect you to know, for example, as you continue on in chemistry here, the mass of like an electron and stuff like that. So those are some values that they probably might want you to know. So let's talk a little bit about protons. Protons, as we just talked about, is found in the nucleus. And each proton has a mass of 1.67 times 10 to the minus 24 grams. If you remember, the electron was like 909 times 10 to the minus 28 grams. In comparison here between a proton and an electron, proton obviously being positively charged, a proton is about 1,800 times heavier than an electron. And that also sort of reinforces what came out of Rutherford's experiment, which was the nucleus is most of the mass of the atom, right? Because in the nucleus we have protons, and each proton that's in there is 1,800 times heavier than any electron that is flying around. So that's an important thing to remember, is a proton is, again, heavier than an electron. Now, at this stage of the experiments, the nucleus is a really small volume of the atom, but it does occupy most of the mass. So you could think of like the atom as like a big football stadium, and like the nucleus is like a marble on the 50-yard line in the middle of the stadium. So a lot of empty space, but it does have this very small, densely populated spot, which is the nucleus, that is very, very positively charged. For a long time, people believed that in addition to protons in the nucleus, there was another subatomic particle. And it actually wasn't until 1930s that the existence of that third subatomic particle came about, and that is our neutron. And a guy by the name of Chadwick did a number of experiments that involved pieces of metal. And what came off of those pieces of metal when he would kind of hit them with some alpha particles were some particles and rays that reflected gamma rays. And gamma rays are no charge, right? Neutral type of rays that are coming off. Later experiments show that they contained actual neutral particles that have a mass of 1.67495 times 10 to the minus 24 grams. Now you might be wondering, why is it going so many places? It is going so many places because if you compare it to the proton's mass that we just saw, the neutron actually just slightly beats the proton in terms of mass. So in terms of mass, a neutron is also about 1,800 times heavier than an electron. And in terms of the most massive, it's actually a neutron is the most massive, followed very closely by the proton. And way over here, electron is the least massive in terms of its mass. So the heaviest of those three subatomic particles are actually neutrons, just barely. Protons pretty close to them. And then 1,800 or so times less massive are electrons. This also again reinforces the idea that came out of Rutherford's experiment that the nucleus, which contains protons and neutrons, they're both 1,800 times heavier than any electron flying around. So it does make sense that most of the mass of the atom is concentrated in that very small volume, which is the nucleus in the middle. Any questions on that? So again, you do need to know, again, for this class, not the exact numbers, but again, the electron does come up along the chemistry journey. But you don't need to know necessarily the exact numbers of the masses of each of those particles for me, but you do need to know that the neutron is the heaviest, followed closely by the proton, and that the electron is the least massive of all of those three particles. Any questions on that there? Come. So here's a nice little chart of that. And again, these things and further experiments just reinforce the idea of our sort of current model of the atom, mostly empty space, very heavy nucleus that contains protons and neutrons, which are the heaviest of the three particles, and our electron flying around at some point. So here's sort of that idea. This is the electron density, that empty space, and this is where we would have our electrons kind of flying around. As you can see, a very small spot in the middle there is our nucleus. And again, this is where we have protons and neutrons, and our electrons are again flying around in that empty space. Once again, as we talked about, there is some attraction between the electrons and the nucleus. And again, that is what kind of holds them there, by the way. That's why they just don't fly away, right? There is that attractive force to the nucleus. Some electrons, as we'll talk about, are held a lot tighter than others. Valence electrons, for example, which are involved in bonding, are the outermost electrons, furthest away from the nucleus. But they're still held there, but not as tight as what are sometimes referred to as core electrons, which are much closer to the nucleus. They get the full brunt of that positive charge, and they're held relatively tight to each other. Any questions on that there? All right. All right, so the chemistry of atoms does come from electrons. They are involved in when we combine atoms to form molecules. If you just think about sort of the location of everybody, if you bring two atoms together and you have your nucleus in each, and on the outside right of that nucleus, we have these electrons flying around. It makes sense those are the ones that come in contact with each other first, right? Because they're on the outside moving around. So as atoms come together, it's all about electrons. We barely ever really never in a chemical reaction touch any of the particles that are in the nucleus. Protons, neutrons never get touched in a normal chemical reaction. It is all about electrons, which make bonds and break bonds. As I mentioned earlier, in nuclear chemistry, it's actually opposite. It's all about playing with those neutrons and protons in the nucleus, and that's why we get different elements that happen in like nuclear reactions rather than in chemical reactions, which we deal with in this class. We never touch the nucleus, so we always have the same elements, what we start with and what we end with. Always the same elements are involved. So let's talk about some of the important properties here of an atom: the atomic number, the mass number, and the isotopes. And let's start with the atomic number. The atomic number is abbreviated with a Z, and it is the number of protons there are in the atom of an element. So if you have a neutral atom, remember that the atom basically has protons, which are positive, electrons, which are negative, and neutrons that have no charge. So if you have a neutral atom, if you know the number of protons, you will also know the number of electrons, right? Because you'll need an equal number of negative things to balance it out. It is super important to remember, though, if you're asked a question of what is the definition of the atomic number, it is only the protons. Yeah, so that is the actual definition of atomic number, the number of protons. But what it will tell you is if you're dealing with something that is neutral, it will also tell you the number of electrons that are present as well. So that's a really important thing. The chemical identity of an atom can be determined solely by the atomic number. The atomic number can be found on the periodic table. It is the number above the symbol. So the number above the symbol is the atomic number. If you look at the periodic table, either the one in front of us or the one to the side, does any of the numbers up on top repeat? They are all different. So every element has its own unique atomic number. And because the definition of atomic number is the number of protons, it is actually the number of protons that is the most important thing in terms of what element you're dealing with. So no element has the same number of protons. So if you're dealing with hydrogen, it's got 1 proton. Yeah? And that is very different than if you're dealing with carbon. It has 6 protons. Yeah? You will never have a hydrogen with 6 protons because that's carbon. Yeah? And just like you'll never have a carbon with 1 proton because that is hydrogen. So it is actually out of those 3 particles that we talked about for the atom, the protons, the electrons, the neutrons, the proton tells you what element you're dealing with. So if you know the number of protons, or you know the atomic number, which is essentially the same thing, and you have a periodic table, you should know exactly what element you're dealing with. All you have to do is go find that number up there, and it'll tell you what it is. For example, nitrogen, if we go to periodic table there, nitrogen is N. It'll be number 7, which means if I have a neutral nitrogen atom, I will have 7 protons. And I will also have 7 electrons because 7 positive things and 7 negative things gives me an overall charge of 0, right? I don't need to worry about neutrons because they have no charge, right? So they can't affect anything. So it's only the protons and electrons that affect charge, but really it's actually just the electrons because protons is what element you're dealing with, yeah? Now the mass number is sometimes abbreviated with an A, and the mass number is the total number of protons plus the total number of neutrons there are in an atom. And that's a really important number because if you take the mass number, which is your protons and your neutrons, and you take the atomic number that we just talked about, which is your protons, and you subtract them, that is how you can determine the number of neutrons. So if you take the mass number and you subtract it from the atomic number, that will give you your number of neutrons. Except for hydrogen. Hydrogen has actually only 1 proton and 1 electron, no neutrons. So hydrogen has 1 proton, 1 electron, no neutrons. Yeah? Everybody else will have protons, electrons, and neutrons. So everybody else will have all 3 of those particles present. When you calculate any of those 5 things, the mass number, the atomic number, the number of protons, the number of electrons, the number of neutrons, those all should be positive whole numbers. So all those things should be positive whole numbers. Can I find the mass number on the periodic table? So I look at this and it says 1.008. I know this is my atomic number. Is this the mass number? What do you think? Is that the mass number? It is not the mass number. And the way you can remember it is a really good way. If you look at the numbers on the bottom, pretty much none of the numbers are whole numbers, right? They're all decimals. And when you do mass number, atomic number, protons, electrons, neutrons, they all have to be whole numbers. So never ever use that for a mass number because it's not. It is actually what we will talk about in a later chapter that is known as the atomic mass, and later the molar mass, like we did earlier today as well. So you can only find the atomic number on the periodic table. How do you figure out the number of neutrons then? You will have enough information given to you to figure out the mass number or the number of neutrons. It will usually be given to you in the problem, but you do not get the mass number there from the periodic table. Any questions on that there? What's that? Yeah, so the atomic number is the number of protons. The mass number is protons plus neutrons. So if you subtract those two, those guys cancel and you're left with neutrons. Yeah. Yeah, so basically to get the neutrons, mass number minus the atomic number. Yeah. So let's talk a little bit about isotopes. So isotopes are, as I mentioned earlier, the same element, but they have different masses. So as we've just been talking about, in order for them to be the same element, what thing has to be the same? Protons, electrons, or neutrons? It has to be the protons, yeah? So protons are the same. So the only way they could have a different mass is actually different numbers of neutrons. So isotopes have the same protons, but different numbers of neutrons. That gives them different masses, and that is also why Dalton's atomic theory, that little part of it, is wrong. Yeah, so that is what invalidates Dalton's atomic theory about all the atoms of the same element are the same, because isotopes are the same element because they have the same number of protons, but they do have different masses. Now, one of the ways that we commonly write isotope symbols is we use the symbol. Top left, we put the mass number. Bottom left, we put the atomic number. So for example, if we did hydrogen, I know it has one proton. I go to periodic table, number 1 is H. And atomic number would be number 1. Mass number here, 1 plus 0 equals 1 for the mass number. Protons plus neutrons. Top there, 1. That would be the symbol for hydrogen isotope. Now let's say I did deuterium. Deuterium doesn't even sound like hydrogen, even though sometimes referred to as heavy hydrogen. I know it's hydrogen because when I look at the description, it has 1 proton. The only person on the periodic table with 1 proton is hydrogen. So even though this is deuterium, its symbol is still hydrogen because ultimately it's still hydrogen. It has 1 proton. It's basically a hydrogen atom. The difference though is it has 1 proton and 1 neutron, which means its mass number is 2, which goes up on top. And lastly, we go tritium, which does not sound like hydrogen at all. It is actually the radioactive version of hydrogen. And I know it is hydrogen because it has 1 proton, which means its atomic number is 1. I go to the periodic table, still hydrogen. I'll go here, and 1. And now it has 1 proton and 2 neutrons, which gives me a mass number of 3 there. And that would be the symbol for deuterium. So even though they have 3 different names, they're all isotopes of hydrogen. They're all essentially hydrogen because they all have 1 proton, and that would be the correct way to do that. By the way, you take the top number minus the bottom number here, it gives you the neutrons. 1 minus 1 is 0 neutrons. Top number minus bottom number, 2 minus 1 is 1 neutron. Top number minus bottom number, 3 minus 1 is 2 neutrons, yeah. So top number minus bottom number will give you the number of neutrons, and that's a very common way it is written. Any questions on that there? Now, what if you have something like this, Cu64? That is an isotope of copper. What do you think the 64 represents? Atomic number or mass number? I know for sure if I go to the periodic table and find copper, it says 29 on top, yeah? And 29 would then be the atomic number, yeah? Which means this is actually the mass number. And that's a very common way isotopes are written. Symbol dash a number, and that number is the mass number. If we wrote this copper the other way, we would put 64 up on top and 29 on the bottom. How many protons would this copper have? 29. It is neutral. By the way, I know it's neutral because there's nothing written there. That's where the charge would be, right? So it is neutral, which means how many electrons should it have? It's got to have an equal number of electrons, right? 29 positive things, 29 negative things gives you 0 overall charge. How many neutrons would it have? It would have 64 minus 39. What you got there? 20, what you got there? 26, maybe? That is so wrong there. I know, that is super wrong. I'm going to go calculator. It is bad.
It's supposed to be 39 or 29?
It's supposed to be 29, I think. That would much better. Maybe that would work better, I think. 35. There you go. I screwed that up terribly, didn't I? There you go. 29. There you go. 35 looks much better there. There you go. I got one of the numbers right. That was not bad, I thought. So yeah, so it should definitely be 35 in that case. Any questions on that there? All right, let's try some here, see how we do. All right, so for each of these, protons, electrons, and neutrons does each of them have? Okay, so let's take a look. So once again, CO is cobalt. Top number is the mass number, right? Which is our protons plus neutrons. Bottom numbers are atomic number, which is our number of protons. Here then, 27 protons we would have. Again, don't see anything written there, so I know it's neutral, so it needs to have a matching number of electrons in this case. So that's going to give us an overall charge of 0, which again is kind of what it has. And our number of neutrons here are going to be 60 minus 27. I wrote the right number this time. That's progress. 33 neutrons in this particular case. Again, top minus bottom. Any questions on that one there? Next one is Cl, which is chlorine. Once again, it's neutral, nothing written there. So we see from our bottom left there, that's our atomic number, which is our protons, so 17 protons. Again, because it is neutral, it's got to have a matching number of electrons to give us an overall charge of 0 in this case. And now our neutrons will take our mass number there, which is 37, minus 17 will give us our number of neutrons. And that's going to be a 20, it looks like there, for our neutrons. Yeah. Any questions on that one there? Lastly, U is uranium, also neutral. And starting with the atomic number, which is 92, which obviously we could get from the periodic table. So 92 protons, going to have, once again, a matching number of electrons to get us to 0. Taking our mass number, which is our top number, minus our atomic number, which is our bottom, will give us our 146 neutrons in this case. Any questions on any of those numbers there? Okay, so let's try a few more here. This one, we want to write the symbol with the mass number and the atomic number on it. Now, clearly in this case, since it doesn't mention anything about a charge or anything like that, you could assume that all these guys are neutral, yeah? By the time we're done, especially when we get into the naming chapter, you'll probably need to know most of the elements that are definitely to the left, to the right, in the middle section. We don't do too much with the ones on the very bottoms, all that much and stuff like that. But ultimately, through our like naming chapters and stuff like that, you'll ultimately usually left, right of the periodic table, and kind of in the center middle part is where we usually see a lot of elements that we do deal with. So at some point, you'll probably know most of those guys by names, especially when we get into naming and stuff like that. Obviously, not right at this moment for this few chapters here, but. All right, so let's take a look here and see how we're doing. So krypton is Kr on the periodic table, and that is number 36 there that we could get. Remember, from the periodic table, we can get this, which is the atomic number. So that's going to help us. So we should have Kr. Atomic number should go bottom left in this particular case. Now we need our mass number. And again, our mass number is our number of protons plus our number of neutrons. So obviously 36 protons. Like I mentioned before, they did give us 48 neutrons, so we can calculate our mass number. Again, we do not want to use the number on the periodic table on the bottom because that is not the mass number, and that would get us 84 for our mass number. Again, whole number is what it should be in this case. Any questions on that one there? Nitrogen, as we saw earlier, is number 7. Once again, what we could get from the periodic table is the atomic number, which is our number of protons. Right? So we know N is the symbol. Bottom left should go our atomic number. Because that is the number of protons, which is 7. Our number of neutrons was given to us at 6. Gives us 13 for our mass number. That should go up on top. Any questions on that one there? Last, we were looking for iron. Iron is actually Fe on the periodic table, and Fe is number 26, I hope still. And once again, that is going to give us our number of protons or our atomic number. So we'll go Fe in this case, 26. In this particular case, they actually gave us the mass number, so we just need to put that in the proper location, top left in this case. It also wanted protons, electrons, and neutrons, so number of protons in this case would be 26. It is neutral, right? So the number of electrons should also be 26, gives you 0. Now, what about neutrons? Neutrons should be 56 minus 26, mass number minus the atomic number, gonna get us a 30 there in this particular case. Any questions on that one there? Questions on mass number, atomic number, protons, electrons, neutrons. You need to be able to obviously find all those things. Since we have this here, let's just for a moment here talk about what happens if something did have a charge, since it's a good place to kind of do that. If something that does have a charge, those are what are referred to as ions. So ions are things with a charge. And there are cations, which are positively charged, and there's anions, which are negatively charged. So for example, if I had my nitrogen, same guy here, 13.7 and a -3, what changes in this case is, will the protons change? They cannot change, because if I change the protons, then it's no longer nitrogen, right? But since it's still nitrogen, the protons cannot change. Neutrons do not have a charge, which means you could do whatever you want with those. That's not going to affect it, right? So when something gains a charge, it's actually the electrons that change. So for here, we would still have for our protons 7, right, which are positively charged. Our neutrons in this case would still be 13 minus 7, which would be 6. But how many electrons would I have in this particular case? I would have 10 electrons. 10 negative things and 7 positive things leaves me -3 left over, right? And that is where the charge comes from. It actually has 3 more electrons than protons. And that's why it now has a -3 charge. It originally started with only 7 electrons, right? And now it has 10 electrons. Again, 3 more than it started with, and that is what happens. This is, by the way, known as an anion. An anion is achieved by something gaining electrons. And as you can see, it started with 7 in neutral, ended with 10, still 7 protons because it is still nitrogen, so you cannot change that. Otherwise, you no longer have nitrogen in this example. How about iron? If I took the exact same iron, and let's just say it had a +3, actually I'll do a +2 charge. Let's do a +2 charge on that. Once again here, this iron has 26 protons, otherwise it would not be iron, right? It still has, in terms of neutrons, 56 minus 26, which would be 30. Now in terms of electrons, how many does it have? It has 24 electrons, right? 26 positive things and 24 negative things leaves you a +2 left over. And that is where the charge comes from, basically. Yeah? So this, by the way, is known as a cation, which is made by losing electrons. If you look at the guy with the charge, has 24 electrons. Guy with no charge has 26 electrons. So if something does have a charge, the only thing that changes in terms of protons, electrons, and neutrons is the electrons. By the way, if you see a negative charge, that thing should always have more electrons than it started with. Yeah, that's what the negative means. By the way, the number is how many electrons it has more, right? -3 has 3 more electrons than the neutral nitrogen. Same thing with the positive charge. If you see a positive charge, it means it has less electrons than neutral. And the number is how many less it has. This guy has a +2 charge, which means it has 2 less electrons than the neutral guy. So the number is how many electrons are involved. Positive is how many electrons were lost. Negative is how many electrons were gained from the neutral atom. And that is how things get charges. Question on that there. It comes from because this thing has a +2 charge. So the only way it could get a +2 charge and still remain iron is because we cannot touch the protons because they're locked into place. So because this has to stay iron, we have basically 26 positive guys locked into place for the iron. We want to end up with a +2 overall charge, which means we actually need to subtract away only 24 negative things, right? So 24 positive things plus 24 negative things leaves you 2 positive things left over. It basically means it now has actually 2 more protons than it has 2 more protons than it does electrons at this point because it lost those 2. It's basic, yeah. So basically, the way you could do it is, iron has 26 protons, right? Positive things, which means if it has a +2 charge, it lost 2 electrons. And when it's neutral, it should have 26 electrons. So 2 less than 26 is 24. Yeah. And the same thing over here. This nitrogen had 7 electrons when it started, neutral. It has a -3 charge, which means it gained 3 electrons. So just 7 + 3 is 10 electrons. Yeah. Other questions? So that is what you do if something does have a charge. Any question on charges? All right. So one of the nice things about isotopes is the chemical properties of elements that are isotopes, and they are the same because, again, most of the time protons don't really participate in any type, or neutrons participate in any type of chemical reactions. So a lot of times people will use radioactive versions of elements, and they will do basically the same type of chemistry in the body, for example, as non-radioactive isotopes. But you can follow the radioactivity and see what happens. So for example, I used to do research with radioactive copper, and we were interested in where copper went through a process. And by using the radioactive version of copper, you could just follow where it went by following the radioactivity. It will do the exact same chemistry as the non-radioactive version of it. So sometimes that's really, really helpful. The next thing we're going to talk about is the periodic table. And this is the periodic table there, and it has a good deal of elements or information about the elements on it. We've got periodic table here and over there on that wall. We've talked about some of the things here on the periodic table, but let's get into it. First off, on the periodic table, there are columns, and these are sometimes referred to as groups most of the time these days. Not too many people call it families anymore. Most people call them groups. When you look at periodic tables, either the one on the wall, that doesn't really have it, or the one we're looking at here on the picture, there's a couple of different types of numbering you'll sometimes see on periodic tables. There's sometimes the A numbering. There's also sometimes the B numbering, and there's sometimes just like the 1 through 18 numbering. For this class and most chemistry classes that you use, we use the A numbering, which is sometimes referred to as the representative numbering. That puts group 1 right here. And by the way, group 1 actually starts with lithium, not hydrogen, and we'll talk why that is in a second. Group 2 is right next door. Group 3 is over here where aluminum is and boron. Group 4, Group 5, Group 6, Group 7, and Group 8. They are technically Group 1A, 2A, 3A. Most people don't use the A when they say it. They just go Group 1, Group 2, and so forth. But it is usually the A numbering. So 1, 2, skip the middle. 3, 4, 5, 6, 7, and 8. Groups go up and down columns on the periodic table. There is also horizontal rows, which are known as periods. There's actually 7 periods, 1, 2, 3, 4, 5, 6, and 7. They go left to right on the periodic table. Those are known as periods. The number above the symbol, as we've been talking about, is the atomic number. And as we saw, every element will have its own atomic number. And you can identify what element you're talking about solely by the atomic number that is present. Now, when we look at the periodic table, it is broken up into 3 categories. There are metals, there are semi-metals, and there are non-metals. So usually on most periodic tables, you could find a staircase, it is sometimes referred to. I can see this one in red and more of a black sort of staircase on the one over there. If you go to the left of the staircase, and not pictured up here, but the 2 rows on the bottom, those are metals. And metals are good conductors of heat and electricity. They're very shiny. They are ductile. You can pull them into wires. For the most part, most metals are solid at room temperature, except for mercury, which is, you can see over there on that periodic table and this periodic table. That one is blue, and this one has like a little green box at number 80. It's actually a liquid, so that's the only sort of liquid that is a metal at room temperature. To the upper right of the periodic table, you have nonmetals. Yeah. It's actually a liquid too. Yeah, yeah. So in that one, they kind of put them as liquids, as blue. Yeah. To the upper right of the periodic table there are the staircase. You have nonmetals. And right on this staircase, and some books include boron, but this kind of twofer down here, these are our metalloids, our semi-metals. This, by the way, is group 1. This is hydrogen. This is lithium. Why is hydrogen not part of group 1? Hydrogen is actually a non-metal, even though it's hanging out over here. So even though hydrogen is hanging out over there in group 1, because that shares a lot of properties with things in group 1, it's actually a non-metal. And that's why group 1 actually starts with lithium, which is a metal. Years ago on older periodic tables, they would actually throw hydrogen on both sides, and you actually see it on both sides of it. But hydrogen actually is a non-metal. And again, group 1 starts with lithium, which is a metal. So that's an important thing to keep in mind. Nonmetals, on the other hand, are the opposite sort of characteristics of metals. They are bad conductors of heat and electricity. They have a more dull, brittle sort of appearance. They also have a more variety of states. Some are gases, some are liquids, and some are solid. And our nonmetals are a lot of those elements, pretty much all of them, that come as diatomic molecules. So if you remember, we talked about hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. All those guys are nonmetals, and all those guys are the ones that come as those diatomic. They come as twos, as we talked about last time. Now, what about our guys there on the staircase? Our guys on the staircase there are metalloids, and they're sometimes called semi-metals as well. They have properties that actually fall between both. And that kind of makes sense based on their location. The metalloids here could have some properties that are very similar to metal properties, and the same metalloid can also have some characteristics that are very similar to nonmetals. So the same metalloid will have some properties people would consider metal type properties, and some that would be considered more non-metal properties, semiconductors, right? Those type of things. So they have properties that fall between them. In addition, some groups do have specific names, and you do need to be aware of that. So starting here in group 1, these are the alkali metals, once again starting with lithium, not hydrogen. So hydrogen not part of group 1, and it is not an alkali metal because, again, it's a non-metal. So lithium, sodium, potassium, those are alkali metals. Right next door at group number 2 are alkaline earth metals. Those are beryllium, magnesium, calcium, strontium, all those guys. By the way, alkali and alkaline, it means basic, as we'll talk about in a later chapter. That's where a lot of strong bases come from, things like sodium hydroxide, potassium hydroxide. So group 1 and group 2, put a little OH on with them. That's where a lot of those kind of strong bases come from that we see. All the way over here to group 7. These are our halogens. These are our diatomic guys. These are our F2, Cl2, Br2, I2. And the last group that has a special name is right next door, which are group number 8. Those are the noble gases, group number 8. And noble gases means, noble means set apart. Noble gases are what are referred to as being chemically inert, which means that they pretty much are unreactive. They'll react with themselves, but other things they won't react with. So they're very, very unreactive. And the noble gases are really important because, frankly, everybody tries to be like them, as we'll talk about in a lot of cases. Here's just a little bit more about those halogens. Again, very reactive. Fluorine, chlorine, bromine. Reactivity actually increases as you go up in the group. Maybe I shouldn't say that today, but it does increase as you go up in the group. Keep that in mind. Fluorine is more reactive than chlorine. Bromine is more reactive than iodine, and so forth. But as was the earlier question, you can see there bromine is kind of a brown liquid that has a little bit of vapor over it. And chlorine and fluorine are gases, and iodines are sort of a purple type of solid that comes out as well. Now, noble gases, which are rare gases, as I mentioned, are really important. Everybody, as we'll talk about, especially when we get into bonding, the whole purpose of all types of bonding is for everybody to be kind of like the noble gases. So noble gases are like super stable. And as we'll talk about with bonding, that's kind of the goal of all bonding, is for everybody to kind of end up like noble gases. The 2 rows at the bottom are set aside so the table is not too wide. This is the lanthanide and actinide series. If you follow the numbering, we go 57, 72. That's 58. This guy technically goes right about there. And if you follow the numbering here, 89, 104, this row technically goes right about there as well. And that is where those guys go. They're called the lanthanide and actinide series because those are the elements they technically should follow on the periodic table. This is perhaps the only periodic table I've ever seen that puts them in the right spot. You can see they're right there in the middle. Those kind of pinky guys right there, those two rows. And that's why they don't typically do it, are over here as well, maybe on this side. Makes your periodic table quite wide when they do that. Transition metals are between group number 2 and group number 3 on the periodic table. And those are our transition metals pretty much all through here. One of the things that transition metals have in common is, as we'll talk about when we get to the naming chapter, is they can actually make a variable type of charge. So for example, iron could be +2 in certain situations. Iron could be +3 in certain situations. Copper could be +1 or +2 in certain situations. So transition metals typically have the ability to make multiple types of charges. That's why these two rows that technically go in here are sometimes called inner transition metals, because that's technically where they should kind of go on there. But most people refer to them as lanthanide and actinide series. Any questions on the location of those things? Now, the characteristic shape of the periodic table basically put elements near each other that had similar properties. They actually left spaces along the way, and they did a pretty good job filling it in. As you move from left to right on the periodic table, you move from a more metal situation into a non-metal situation. So more metal as you go upwards and to the right, more non-metal type of characteristics obviously happening. Any questions on the periodic table? Yeah.
How come the first guy was so
It really is for this reason. Just makes the periodic table too wide. Years ago, they used to put periodic tables on books and stuff. Your periodic table would take up the entire cover and stuff like that. So it is as simple as that reason. Also, a lot of times not used a lot of those elements. These are where you find a lot of man-made elements like Einsteinium, Nobelium, Californium, Berkelium, all these kind of things. These are all a lot of radioactive elements as well. So a lot of these guys, especially the bottom row there, they kind of put them down out of the way. And most chemistry classes not used a lot. You'll use it a little bit when you go to 1B, you do nuclear chemistry chapter and stuff like that, but a lot of times we don't use a lot. But a lot of the man-made sort of elements are kind of down that way. Yes, in the back. They're technically sometimes referred to as inner transition metals. Yeah, most people would most likely classify them as lanthanides and actinides. Is really the probably most common classification they would give it. Yes. We'll talk about electronegativity a little bit later in a different chapter, but there is a trend in electronegativity. Yeah, no, it's electronegativity increases to the right and decreases to the left and down and stuff. Yeah. Other questions? Okay. All right, so let's talk a little bit about elements. As I mentioned before, noble gases are pretty stable. That is what essentially everybody is trying to achieve. There's also some metals that are considered noble metals. So gold, silver, and platinum, they're pretty unreactive metals. You could hit a gold with a lot of things and it won't do anything. So you hit gold with some like nitric acid, it's not going to have a problem or anything like that. So it's very, very unreactive. And that's what sometimes refers to those guys as noble metals. That's right about here. Those guys right there. Those are the metals. All right. And again, just some characteristics of noble gases and our noble metals. And like I said, as we get going into sort of bonding and all that kind of stuff, this is ultimately the goal of really everything is I want to be like the noble gases, because the whole goal of all chemistry is to be stable and low energy, good electron configuration like the noble gases have, and that's the goal of bonding, as we'll talk about. We talked about diatomic molecules. Obviously, there are those 7 that are nonmetals, or are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. And again, some characteristics of those guys, all nonmetals. And again, you can see the variable sort of states, gases, liquids, and solids happening. All right. We're actually going to skip this, I think. Let's talk a little bit here to finish up on ions. So we touched upon it when we were doing our electrons, but a reminder that an ion is basically something that has a charge. And as we saw when we were talking about our electrons, protons, and neutrons, it is the electrons that change to give somebody a charge. So there are cations and anions. As I mentioned earlier, a cation is essentially something that has a positive charge. So if we look at sodium, sodium that is neutral has 11 protons because its atomic number is 11. It will also have 11 electrons, and that gives us our 0 charge. Sodium, which is group 1, will make a +1 charge. So in order for it to still be sodium, it has to have those electrons locked into place at 11. But because it's a positive charge, did it lose or gain electrons? It has lost electrons, right? Positive is what that means. +1 means it lost 1 electron. So instead of 11 electrons, it now will have 10 electrons. 11 positives and 10 negatives leaves me a +1 left over. And again, that is where the charge comes from. In this case, sodium ion has more protons than it does electrons. And overall, that's going to give it a positive charge. That is, again, is what is referred to as a cation. And if we look at something like magnesium with no charge, magnesium's number 12 on the periodic table, 12 protons, well, it has to have 12 electrons, giving us a 0 charge. Now, magnesium with a +2 charge means that it has lost 2 electrons. So really, you could just look at the protons. It's got 12 less 2 is 10 electrons. So we'll get you there. And that will give you +2 left over in this situation, which is where the charge comes from. Aluminum is neutral, 13 atomic number, would have 13 electrons, and that would be 0. Again, aluminum with a +3 charge, 13 protons, +3 means lost 3 electrons. So it has to have 10 electrons at this point. 13 positives, 10 negatives, give me a +3 overall charge that's happening in this case. So again, anything that has a positive charge is known as a cation, and it's achieved by, as you can see, losing electrons equal to its charge, ending up with more protons and electrons. By the way, how do you name something that is positively charged that's a metal? You frankly just use the name of it and put ion at the end. So Na is sodium. This would be sodium ion. Mg is magnesium. This would be the magnesium ion. So you basically just use the whole name of the element and put ion at the end of it. You could also represent somebody losing electrons in a reaction. So if you have sodium, it will make a sodium ion plus with a +1 charge, and it will lose an electron. And you will see electrons on the product side. And that indicates that the electrons are being lost or given off. Same thing if we look at the magnesium like you have there. Magnesium going to magnesium with a +2 charge and giving off 2 electrons in this case. And again, because the electrons are on the product side, that indicates this is how the cation is being formed and those electrons are being given off. Any questions on that there? Now, an anion, as we talked about, is the opposite. It is when somebody gains electrons. And if we look at chlorine, chlorine is number 17 on the periodic table, so it's got 17 protons. With no charge, it would also have a matching number of electrons, which would be 0. Chlorine, when it gets a charge, is -1, which means in order for it to still be chlorine, it's got to have 17 protons. Negative means I gained electrons, and 1 is how many I gained. So I just add that to my atomic number, and that gives me 18 electrons. 17 positives, 18 negatives, leaves me a -1 left over. And that is, again, where the charge comes from. If I look at oxygen, oxygen is number 6 up there, I'm sorry, 8 up there on the periodic table. And it has 8 protons. It would also have 8 electrons if it is neutral. Oxygen, when it gains a charge, makes a -2 charge, which means it has now gained 2 electrons. So it would have 8 protons to keep it at oxygen. 8 plus 2 is 10 electrons. So you could either add or subtract from the atomic number your electrons, as long as you know plus and minus means, and it will get you your -2 left over, which is the charge. How do we name things with negative charges? We actually put IDE at the end of it. So this guy here, Cl minus, would be the chloride ion. Oxygen would be with a charge, the oxide ion. So that is how negatively charged ions are named. Put IDE at the end of the name. Get rid of the last part of the name, sometimes more or less of the last part. We obviously will talk more about that when we get into real naming. Just like with the positive guy, you could represent the negative guy with an electron on the reactant side. And that would be like it is being gained. Same thing here with oxygen. You would put the electrons on the reactant side like it's being gained. So if you want to represent sort of that guy gaining an electron, you could write an equation like that where electrons are on the reactant side. Question on things with charges. Now let's talk a little bit about charges and the periodic table. Now, first off, the thing that you should keep in mind for sure is things on the periodic table, like I talked about maybe last time as well. If it is by itself, if it is not combined with anybody, it is just by itself, they do not have charges. So sometimes people think everybody always got a charge on the periodic table. Things only get charges actually when a metal and a non-metal come together. And that's actually when they get charges. But things, if you just have sodium by itself, no charge. If you just have copper by itself, no charge. Just have chlorine gas by itself, no charge. So things that have charges are really, as we'll talk about, ionic compounds, and that's when metals and nonmetals come together. But when things do make charges, there are certain things that have fixed charges. Everybody in group 1, starting with lithium, will always make a fixed charge of +1. So they will always make a +1 charge. Everything in group 2 will make a +2 charge in terms of what it normally will make. Coming over here to group 3, really it's aluminum. +3 is mostly what you have. There really is no good pattern because that's your staircase kind of coming down through there. We actually skip group 4. And at group 5, where our nonmetals are, -3 for our nonmetals. Yeah, for the nonmetals. Group 6, -2, again for the nonmetals. Group 7, -1. So it's kind of like +1, +2, +3, skip, -3, -2, -1. So go 1, 2, 3, skip, go backwards, 3, 2, 1. And again, we're talking about on the minus side, non-metal region, because what's below the staircase are actually metals, yeah, and they're positively charged. So we're talking about negatively non-metals above it. By the way, the transition metals have various charges like we talked about, but there is actually 3 members of the transition metals that have fixed charges, and that is zinc and cadmium. These guys will have a fixed charge of +2, both of them. And if you hang a left at cadmium, you'll hit silver. Silver is +1. So even though those 3 are transition metals, they will actually have fixed charges. Cadmium and zinc being +2. And again, hanging a left there, silver going to be a +1.